Oh, sweet gauge of mine. Oh, you guys are back. It's time to talk about strain gauges. So I think strain gauges are just devices that allow us to measure the normal strain in a particular direction. And this is very useful for engineers, especially if we're running like an experiment or we're trying to see how something is performing in real life. We need to apply strain gauges to figure out what's exactly happening. Once we solve, we're able to determine the strain at a particular patient, we can always then use our mechanics equations to find stress. We can do plane stress, we can do plane strain depending upon the case. We can do transformations, principal stresses. We can check if failure has occurred. It gives us a variety of tools to check the real-life performance of engineering systems and structures. All right? So I want to tell you a little bit about what a strain gauge is. A strain gauge looks like this. This is a blown-up picture of a strain gauge. And it has a couple different parts. So first, we have to have some wires that frame into this strain gauge. So the wires come in, and we would call these like the electric current, or the lead wires, whatever you want to call them. Lead wires. I want you to think this is our electric current. Current's going to come in one side. It's going to go through this sort of coiled wire. So I'll call these the gauge wires. You're going to run through this wire and then it exits back and goes back to your excitation device. All right, what does this allow us to do? How do we measure strain? Okay, so as we extend, if we were to attach this, and we basically just glue it to something, we adhere it to a surface. As this extends, the length of this wire is going to change. We refer to this length as the gauge length. Overall, this wire is going to extend. And so that means the wire's total length is longer. If you go back to like physics 2, you can relate electricity and resistance. Remember voltage and resistance. And depending upon the length of the wire, it will change the resistance that is experienced. So if we're measuring the current, the voltage, the excitation, the voltage in, and then we measure and compare that to the voltage out, we can figure out the change in resistance of this wire, and we can equate that change in resistance to strain. Okay? And so that's how this works. We glue it down by attaching this back part. We call this the gauge backing. We glue that to the surface of the material in which we're looking to test to measure the strain. So we attach this gauge. You can see I've attached a gauge here on a particular steel casting. So as part of my research, we were testing this connection, and I wanted to find the strain in my connection in the vertical direction. So I wanted to find a normal strain, epsilon, in a particular direction. So I attached a gauge, and then I covered it up with wax here because we don't want to leave the surface exposed for too long if we're going to leave this up for days and days and days. If you're going to just attach the strain gauge and then use it pretty quickly or within a short period of time, it'll be okay. But I had this set up over weeks, so I wanted to prevent damage. So you just kind of cover it up. But we were pulling on this. I was able to measure the strains in my casting. I was able to compare that to the strains that I predicted and the stresses I predicted in my computer model. All right, so that hopefully gives you a little bit of an idea of what strain gauges are. I have a few here with me to take a look at. So this in particular is the basic strain gauge. So hopefully you can see that in there. They're pretty small devices. And And so here is also a gauge that's attached. So in one of our laboratories, we'll attach strain gauges to these rulers, and then we'll use the rulers in a future bending stress laboratory to check the strains in this aluminum ruler as we bend the ruler. But you can see the gauge is attached. Again, it's basically just super glued to the surface. All right, more information about strain gauges, please let me know. I'm happy to answer any questions you might have. But that's the basic of a strain gauge. Next, we're going to talk about strain rosettes. When we talked about plane strain transformation, we involved epsilon x, epsilon y, and gamma xy. Right? So when we look at measuring this with strain gauges, because we need to solve for epsilon x, epsilon y, and gamma xy in a lot of our applications, it's important that we have more than one strain gauge applied. That's the idea behind a strain rosette. So in a strain rosette, we have 3 strain gauges. And what that's going to allow us to do is it's going to allow us, once we apply a rosette on a particular plane, we are able to identify epsilon x, epsilon y, and gamma xy in that plane. All right, here is an example of a strain rosette. So hopefully you can see those inside the package there. Otherwise, we also have a big image of the strain rosette on the board. This would be maybe a 45-degree strain rosette because each of these are rotated at 45 degrees. It's important that we don't have them all in the same direction, or else they're just going to measure one strain. They have to be in different directions. So let's see how a strain rosette works. The basic idea is a strain rosette consists of 3 different regular strain gauges, basically. And so I can then look at the angle to each of these gauges. So if I consider this as gauge A, and this is my line of action for gauge A, I then have an angle from the x-axis. I have an angle up to here that we'll call theta A. Now I can repeat the process for gauge B, call this theta B, and for gauge C, call this theta C. Maybe I'll do a lowercase b here so it matches up with your notes. The way we solve for epsilon x, epsilon y, and gamma xy is by applying our strain transformation equation to each gauge. Now I want to apply the first version of the epsilon x prime equation that we derived in our notes. So this is it right here. And we're going to basically apply this at each gauge. So I would say that the strain in gauge A is equal to epsilon x cosine squared theta A plus epsilon y sine squared theta A plus gamma xy sine theta A cosine theta A. Okay? Straightforward. We do that for gauge B and for gauge C. So these values, A, B, and C, are measured using our experimental data. So we're actually measuring the strain, epsilon A, B, and C, from our test. We also know theta A, B, and C. Theta A, theta B, theta C, known from geometry. So we either applied the strain gauges at a particular geometry, or we used the standard geometry as part of the strain rosette. Since we know all the thetas and all epsilon A, B, and C, the variables we don't know are epsilon x, epsilon y, and gamma xy. You guys are astute mathematicians, so I know that you recognize that there are 3 equations here and 3 unknowns. And so you're able to solve for epsilon x, epsilon y, and gamma xy. Once you have these three values, epsilon x, epsilon y, gamma xy, we can go on to determine principal strains, max shear strain, all those other things that we did using our strain transformation equations. So once we have epsilon x and epsilon y and gamma xy, we can run through any or all of these equations to solve our engineering problem. All right, so let's take a look at example 2. In example 2, we're asked to measure the strain on an axle or any sort of plane, especially we're looking at 2D strain. So we have a strain rosette attached, a 60-degree strain rosette. Basically, gauge A, B, and C are separated by 60 degrees. We have the values for the measured strain, and we have to determine a few quantities, the in-plane strains and the principal strains and the max shear strain. So the way we're going to solve this problem is by applying the strain transformation equations to each gauge. So I want to take the values from above those three equations, and I'm going to apply them to these three gauges. Again, theta is going to be the angle from the global x-axis all the way around to wherever that gauge is lined up. So in this case, theta A is going to be 60 degrees, theta B will be 120 degrees, and theta C will be 180 degrees. To solve for epsilon x, epsilon y, and gamma xy, we just need to plug in the measured values of epsilon A, B, and C, along with theta A, B, and C, into the three equations at the top of the screen, and then we'll have a system of linear equations, three unknowns, and we'll be able to solve for all three of these variables that we desire. I'm going to fast forward through this information, but please feel free to pause it so you can get it written down in your notes if you like to have it, or just know all we're doing here is a little bit of math. I hope you're not panicking in trying to solve this. I do want to give you a little bit of help. Sometimes if one of the gauges lines up with one of the directions, we can see that it'll cancel out. So we see in the equation for epsilon C, we get cosine 180 is going to be negative 1 squared, gives us positive 1, and sine 180 gives us 0. So from the last equation, we can solve that epsilon x equals 200, which is the value from gauge C, 200 times 10 to the minus 6 in terms of our strain. If you struggle with writing this out or doing it on your calculator, I'd encourage you to check out the website Wolfram Alpha. So here I've gone to it, I've typed in system of equations, and it's given me three equations that I can enter. Now I had this one saved, so you can see this is equation A. So I have the negative 300 equals, and I go through, and x equals epsilon x, y equals epsilon y, and z is going to be gamma xy. So I want to solve this system of equations for x, y, and z. Once I wrote it out the first time, it was easy to then just kind of copy and paste that below, and I can change the value for epsilon b as well as the angle, and then I can copy and paste this into the third equation, again changing the value for epsilon c, and then changing all of those angles to 180 degrees. So this is just another tool for you to have. I'm happy in my class if you go ahead and use this tool to solve these systems of equations. It's freely available for you on the web. All you have to do is type it in, you hit go, and you'll get the answers. They also often give you like symbolic answers, or even we got like exact answers. So here we see x is 200 as we expected. Epsilon x was 200 times 10 to the negative 6. We see that the value for y, which is going to be epsilon y, is going to be negative 533.33 times 10 to the minus 6. And we also see that gamma xy, when you evaluate that equation, will come out to be 115.470 times 10 to the minus 6. So I'd encourage you to take these three equations and three unknowns and maybe give it a little practice if your algebra is a little bit rusty. Otherwise, also encourage you to check out other available tools like Wolfram Alpha so that you can solve this system of equations and get to our answers for the in-plane strains. Once we have epsilon x, epsilon y, and gamma xy, we can go ahead and we can solve for the in-plane principal strains and the in-plane maximum shear strain. So just go ahead and reference the equations. For the principal strains, it's going to be the equation for epsilon 1, 2. Again, we have a plus and minus in there. I'm going to write and break this out into two components so that I have the value under the square root. Because when we get to the max shear strain, we're going to need that number as well. So we see epsilon 1 equals 204.518 times 10 to the minus 6, and epsilon 2 is negative 537.851 times 10 to the minus 6. And for the max shear strain, we see it's the value under that square root. So the max shear strain over 2 will equal 371.184. So I multiply that by 2 to get gamma max. Gamma max is 742.369 times 10 to the minus 6. I hope you found this example instructive on how we can use strain gauges in arbitrary directions to then measure epsilon x, epsilon y, and gamma xy. We can see that this has a variety of applications in engineering, and I hope you enjoyed doing it, and I look forward to teaching you in the next video.